Hello, everyone. Thanks for coming to our presentation. And I'm Juan, one of the creators of Horus. So this presentation is going to be divided in 6 sections. First, I will introduce the problem that Horus solves by using a real-world scenario. Then my colleague Rich will give context into the engineering area that is needed to solve the problem, observability and telemetry. After that, Callie will list a couple of existing solutions and explain why they are not perfect for our use case. She will also show a demo of Horus being used. Next, Jose will describe the architecture of Horus and demonstrate how to easily deploy it with Docker and NPM. Then I will explain some implementation challenges that appeared when developing the project. And finally, I will also explain some future work that could be done in Horus. First of all, what is Horus? So Horus is an open source observability solution for microservices. Users can generate, store, and visualize correlated telemetry data, metrics, and traces, allowing them to see the real-time health of their application. This allows for easier finding of bugs and errors for the developer. If you haven't understood most of this, don't worry, because we'll cover each part in the following sections. But before we do that, let's introduce Evo T-shirts. It's an e-commerce site that has recently skyrocketed in popularity. What started as a one-person side hustle has now outgrown a monolithic architecture. This means it's time to move to a microservice architecture for better organization. Oliver has led a team of engineers who built Evo T-shirts for years, and he continues to oversee each sub-team in their now assigned microservice. One day, he wakes up and finds that the site has been inundated by a stream of bad reviews overnight. What happened? Customers are complaining about not being able to buy products, and many of them sign off swearing they will never try the site again. While Oliver is confused, the CEO wants answers. Different people, different teams, go on to buy some t-shirts as if they were real customers. The problem is that some of them can complete the purchase without errors, whereas others do experience errors. It's hard to recreate the problem, as there are inconsistencies when looking for it. If they can find what the problem is, they can start looking for a solution. Oliver's last resort is to look at the logs of each microservice, hoping they will contain useful information about the alleged errors. Unfortunately, the logs look like what you see on the screen. The problem is that logs provide too much information in an unstructured way. As Oliver scrolls through them, his frustration grows. The logs are endless and difficult for him to parse. He sees something about an error here and there, but it's unclear what is happening or why. Oliver needs an observability tool to know what's going on. So before we continue with Oliver and Evo T-shirts, my colleague Rich will give some context into observability, telemetry, traces, and metrics.
Brilliant, thanks, Juan. So observability is the technical domain that Horus exists in. So it's important we take a moment here to explore what observability means and begin to get to grips with how observability could solve Oliver's problem. So firstly, it's defined as the ability to measure the internal state of the system only by its outputs. So what this means is in order for us to detect the status or health of a system, we need to turn to these outputs to get a better idea of how an application or system is operating. By referencing this data, the developer can easily navigate from effect to cause in a production system. So what's the difference between observability and monitoring? Well, observability is designed to allow the developer to ask theoretical questions about their infrastructure, and they have the tools to be able to actively investigate and resolve an issue rather than just consume information passively. Observability allows you to ask questions like, what is most likely contributing to latency right now? Where and when are my users encountering errors? And what's the health of my application currently? So what exactly are these generated outputs that I keep referring to? Well, in the world of observability, this data is referred to as telemetry. Telemetry is typically defined as the collection and transmission of data to receiving equipment for monitoring. In essence, it's a historical byproduct of a system's operations in the form of useful data. There are three different types of telemetry data, which are known as the three pillars of observability. They are metrics, logs, and traces. We'll be getting to know these three data types in greater depth later on in the presentation. Ultimately, these data types are the building blocks of observability. By building relationships between them, we're able to gain insights into the history, trends, and interactions that are taking place in our infrastructure. In the publication Software Telemetry, Jamie Wiedezel describes observability as systems that bring you telemetry and display it in a way that will help you make decisions. Wiedezel later goes on to explain in his book that any telemetry system is essentially a data pipeline, and this pipeline is composed of three major stages: emission, shipping, and presentation. So what it will do is it will ingest data, process it, store it, and make it retrievable to the end user. What we're going to do is take a look at each of these stages individually so we can see what happens at each stage and how they interact with one another. So the emitting stage is the first stage in the telemetry pipeline. It's responsible for generating telemetry data in a production application. The types of telemetry that could be generated are typically from three different sources. You have production code, hardware that's running that code, or external software that's being used as an additional service. The emitting stage is typically achieved by injecting an SDK into the production code, which will instrument and aggregate the telemetry data. You can also add context-related details at this point as well to the telemetry that you're generating to make it easier and understand to interpret when it arrives on the other side. Some real-world examples of this include Jaeger for tracing, Prometheus for metrics, and OpenTelemetry, which is fast becoming the gold standard in telemetry generation and processing. The shipping stage is responsible for receiving the raw telemetry data from the emitter. Its priorities are to process it into an accessible data format, enrich the data if needed, and save the data in a storage mechanism to be used by the presentation layer later. An important design factor of the shipping stage is to consider how to organize and store the raw telemetry data that is generated by your emitter. Telemetry data by nature is generated continuously and at a very high frequency. So your database of choice needs to be able to handle this high write intensity while also being able to query the data when required. If the frequency of the incoming data is beyond the processing power of your database, it's a wise decision to consider the implementation of either a queue or an event bus to manage that data influx. Finally, we've got the presentation stage, and it's the last phase in the telemetry pipeline, and crucially, the only one which most stakeholders will interact with to make important design and business decisions. The presentation stage's purpose is to transform telemetry data into useful, measurable, and human-friendly visuals regarding how an application is performing. Interestingly, the presentation stage is often a separate architectural component to the emission and shipping stages, and is regarded as the user interface of telemetry architecture. It's also often what large SaaS uses their primary selling point. It's their dashboard, it's their UI. In essence, telemetry presentation is always a key component of telemetry architecture, even though it does not directly impact the generation of telemetry data. If the architecture doesn't implement the stage itself, the user will just do it themselves, either by creating their own graphs or outsourcing to a separate UI component like Grafana. Brilliant. So we've explored the full extent of the telemetry pipeline. Let's turn our attention back to the telemetry data, metrics, traces, and logs, and their differentiating qualities. So a metric, it's defined as a value that expresses some data about a system. These metrics are usually counts or measures and are often aggregated or calculated over a period of time. So for example, this could be an aggregated measurement of how many requests took place in the last 10 seconds. Metrics can answer questions like, is the application performing slower than it should be? Are users encountering errors while using the application? And at what time of day are we receiving the most amount of requests? Why an application is behaving in a particular way may still be unclear. But what metrics give us is the broader picture of an application's overall state and performance. A request can pass through a host of different services, making them harder to pin down and understand what really happened. A trace provides a view of this request throughout its lifetime in a system, where it starts, where it goes to next, and where it finally terminates throughout a distributed infrastructure. Traces also capture each step of the way and how long each step took. This is commonly referred to as a span, which is shorthand for a span of time. Traces are the newest telemetry data type and are less common than metrics and logs. What they are great at, and what's really their superpower, is providing context for their other telemetry counterparts, which generally tend to operate at this higher level of abstraction. In essence, traces give us this low-level perspective of an application's history and let us see the greater details of what's taking place under an application's hood. Finally, we've got logs, and logs are structured or unstructured lines of text that are emitted by an application in response to some event in the code. Logs are the most detailed data type, so it's easy to assume they're immediately helpful, and they can be, but all the details can make them hard to parse and understand and to store. Logs are great when diving into the details and seeing a step-by-step explanation of what a system did or attempted to do. So, which of our 3 telemetry data types should we use to solve this problem? Operate at the macro level. They aggregate all monitoring measurements and export them at specified time intervals. And what's great about them is this exporting cost does not increase with higher application traffic. This is a great place to start. But there are some limitations in taking a metric-only approach. If an application were to start detecting errors, or there was a sharp increase in overall latency, you wouldn't be able to identify where across your infrastructure the complications were materializing. Traces are the natural counterpart here. They provided contextual information around the journey of a request and how it unfolded as it moved through a system. This can help pinpoint the source of an issue in a distributed system quickly and accurately. By establishing a relationship between the macro nature of metrics and the detailed nuances of traces, the user could theoretically jump between a high level and a low level perspective by switching between these 2 different telemetry data types. So now we have a greater understanding of how observability can be achieved through telemetry. I'm going to pass you to Callie, who's going to remind us of the problems that Oliver's facing and what solutions exist that could help him out.
Thanks, Rich. So when we left Oliver and his team, they were facing a few different issues, but mostly they came down to they were getting customer complaints that Evo t-shirts wasn't working. Some people were more descriptive, saying things like, my cart isn't accurate, or I can't complete the checkout transaction. Others were just saying things like, your website doesn't work, I hate it. So some people on his team were able to recreate some of the problems, like, oh yeah, my cart isn't accurate, but then other people were able to have an accurate cart. So they weren't able to consistently recreate the problem in order to pinpoint what was happening. So even if they have a suspicion of where the problem is, they can't necessarily fix it, because if they quote unquote fix it, is it really fixed, or were they just not able to regenerate the problem at all? So because they don't know where the problem is, they can't fix it, and they're stuck with a lot of grumpy customers. And this is where observability could really help out Oliver and his team. If they were to run an observability system alongside their application, the observability system would be generating that telemetry data that Rich was just telling us about. Specifically, if they had metrics and traces that were correlated, they'd be able to use that to find where the issue was happening. So if their metrics were generating things like requests per second and errors per second, they would be able to see the errors happening. They wouldn't have to wait for a customer to say, hey, your store isn't working. They'd be able to see it within seconds of it actually happening. But they wouldn't have to stop there. They wouldn't have to stop with saying, oh, there's errors in our application. I really wish I knew where they were. Instead, they could look at the correlated traces and see the literal user path that they went down to generate that error. So the focus wouldn't have to be, let me recreate it immediately. They'd be able to see what actually caused the error. It might be a 500, there might be a 404, there might be some weird payload and a post request, whatever it may be. The trace would allow the developers to see that information. Then they could see where the problem is and go about fixing it. So because observability can really help Oliver and his team, it's a great thing for them to do. The next natural question then is, how should they have an observability system? So Oliver and his team are software engineers. They can figure out observability and telemetry, and they can maybe put something together themselves, but that's not what they're interested in. Right now, they're not interested in mastering observability. They're interested in using it. So the best thing for them to go to is an all-in-one service, something they can get up and running, provides everything they need, and it just works. So the best place for them to start would be with a SaaS solution. Two of the biggest in this domain are New Relic and Datadog, and they have some great pros right off the bat. First, they have this out-of-the-box full observability platform. You don't have to patch something in, it's all there. All you really have to do is copy some instrumentation, a few lines of code into some files in your code, and it works. You don't even have to necessarily really understand how it works because it just works. A lot of the complexities abstracted away, things like what database are they using or how do they query the database? You don't have to know that because they take care of it for you. And the way you interact with your data as a developer is with a very polished UI that has more features than you could possibly use. And so all of those are really great things for them. However, there are some immediate drawbacks for Oliver and his team. The first is the high cost. New Relic and Datadog will cost $2,000 to $11,000 a month for a small engineering team, which is totally understandable for a much larger corporation or company, but it's really out of bounds for where Evo t-shirts can afford right now. If they would go down the free route with either one of these, they'd have to give up ownership of their data, meaning if they left New Relic, they'd have to leave their data behind. Also, if they wanted to do some analysis that goes back further, maybe like 2 weeks, they wouldn't be able to do that either because the data is automatically deleted after 8 days. And although the UI is very feature rich and very, very polished and nice, it would require some more devoted time to really understand all the features. They have very good documentation, but again, it would take time to really master this and figure out to find what they need. And that's just time they don't really want to spend right now. So because SaaS doesn't work out for Oliver and his team, they might try to go another direction, which is a DIY approach. On the screen are just a few of the different technologies and open source projects that are used in the sphere of observability. The punchline is this, though. In order to put something together, they have to deeply understand it. They have to understand what each of these technologies do and don't do. For example, not all of these work very well together. So Grafana can query timescale for metrics, but it can't query it for traces. Grafana can query Jaeger for traces, but then Jaeger needs Elasticsearch or Cassandra. OpenTelemetry can work with timescale with traces, but then Grafana can't get the traces from OpenTelemetry through timescale. You don't have to remember all those details. The point is just, it's confusing. And the way that you figure this out is by spending lots of time mastering it and putting these things together. And again, Oliver and his team could, but they don't want to spend the engineering cost and the time in order to make it happen. So for right now, this is where Oliver and his team are. They like some things with DIY. They like the idea of keeping their data. They like that it's not super expensive, but the draw of SaaS and how easy it is to set up is also really nice, but they don't have the cash to be able to afford that. So what Oliver and his team, what they actually need and what solves these problems for them is Horus. And so let's look at that now and why that can help them. At a high level, Horus is an open source observability solution for microservices. Users can generate, store, and visualize correlated telemetry data, allowing them to see the real-time health of their application. Now, that's a lot of words. So let's break it down and extract some meaning from it piece by piece. First is that Horus is an open source observability solution. It's open source, so the code is free. Yes, you have to pay to store your data from your telemetry data, but you'd have to do that no matter where you go. It's open source also in that the code is unlocked, as it were. If people on Oliver's team want to look closer at how things are really working under the hood, they can go about doing that. Maybe down the line, there's another feature they want to add that Horus is almost there, but they just find a need later that just goes right beyond it. They're welcome to develop that further and make it really fit their use case even better. But Horus is also a complete project, so they don't have to understand it. They don't have to go about going into the code and doing all that. And this allows them to understand it as little or as much as they'd like. The next thing Horus does is it generates and stores telemetry data. Specifically, it uses OpenTelemetry to generate, and it uses timescale to store. In the next section, Jose will talk a little bit about OpenTelemetry and timescale and why we're using them. The last part of Horus, and Rich mentioned in the presentation stage, this is the main place people interact with an observability product, and that's the same for Horus. This is where you can visualize correlated telemetry data and see the real-time health of your application. Here's a little GIF of the UI, but let's actually take a closer look at the UI. So this is the first page of the Horus UI where you can see your metrics. You have total requests per 10 seconds, errors per 10 seconds, as well as the latency health. And on the top right, you can choose different time frames relative to where you are. You can also click the refresh button just to make sure you're really getting up to date, the real 10-second data there. When you hover over a data point, it'll show you how many requests are in that time. And if you click on a data point, it will take you to the second page. These are all the traces that happened in that 10-second interval. You can filter them, you can sort them. And this kind of gives you a high-level view with some of the details that each of these traces have. But if you want to understand the full journey of an individual trace, you can click on any one of these. It'll take you to the final page. And this has a breakdown of all the spans. It defaults to HTTP spans in the top right there, but you can change that to non-HTTP spans. And of course, you can look at all the spans as well. And if you want even more detail, you can click on any of these spans and it will show you the attributes of what happened in that span. What was the action? What was the status code or the method? What really made up the details of that? And anytime you can hide that and see the waterfall chart again. Now, if you want to look at a different trace, you can click back to where you just were. And of course, you can go back to the main page and start the journey all over. In summary, Horus is really good for Oliver and his team. And it's because Horus is open source. It's an all-in-one service. It has the flexibility and the low cost of DIY, but it doesn't have the high engineering costs. It's already all there put together for you. It's easy to deploy. It has a simple UI that includes everything that they need right now, but nothing to distract or overwhelm them. And it has that clear connection and correlation between metrics and traces. Now, Horus isn't all things to all people, and it does give up certain things like hosted storage or all the other features that things like New Relic and Datadog provide, but that's okay for Oliver and his team, and it fits what they need right now just fine. In the next section, I'm gonna hand you over to Jose, and he's gonna talk a bit more about the Horus architecture and why it is how it is.
Thanks, Callie. So you've already spoken to us about why there's a need for something like Horus and how Horus behaves. I'm now going to answer a different question, which is how Horus is built and how Horus is deployed. So let's first start with how Horus is built, and let's look at this high-level overview of Horus. So on the left-hand side, you have a general microservice application that has a root service. So it's that box with those 3 services to the left. And those services post telemetry data to the Horus infrastructure that's on the right. So Horus runs on a single VPS that has a Docker network. And within that network has 4 Docker containers with each component communicating between themselves. But there's a lot of information. So let's break this down piece by piece and understand how this works. And let's first start with going back to Evo t-shirts. So this is just an example of how their microservice application, or at least a part of it, could work. The customer hits the root service with an HTTP request, which then uses other services in order to fulfill the operations the customer is expecting. Now, the problem with this for Oliver and his team is that a general HTTP request cycle doesn't generate that telemetry data that we've spoken about. It doesn't generate those metrics and traces we need to work with. So that's where Horus Agent comes in. So Horus Agent is an NPM package that we've developed using OpenTelemetry tools. We chose to work with OpenTelemetry because it's the rising gold standard for generating and working with telemetry data. It's backed by most industry players, and crucially, it allows you to, with a single technology, as in OpenTelemetry, generate different types of telemetry, like metrics and traces and logs. So those were key considerations for why we chose to work with OpenTelemetry. So when you install our NPM package for Horus Agents, what it does is it helps you instrument and install the exporters and the instrumentation to generate that data. In this case, this is how the code looks like when you do it. It takes about 5 minutes, up to 5 minutes per service between installing the NPM package and placing this code. It's about, like you can see, less than 10 lines of code, and this is just for the root service. When you go to the dependent services that aren't the root service, it's even less code. It's just 2 lines of code to generate those traces. So this is how Evo Teacher's application would now look like. By placing that Horus agent that is in purple, what the application now is doing is those HTTP request cycles are now generating that telemetry data, and that can be used in Horus. But let's break this down a little bit more by looking at the distinction between the metrics and the tracing agents that are provided here. So this first part is the metrics agent. This is installed with auto instrumentation from OpenTelemetry, again, using the NPM package that I showed before and explained. And what it does is it generates metrics every interval. And specifically, we've created our NPM to generate 3 types of metrics that you saw when Callie explained it: the requests per second, the errors per second, and the latency per request. And besides the instrumentation that generates those metrics, what it also has is an exporter that exports those metrics and sends it as a post request to the Horus connector, which I'll talk about briefly. Now, if we go to the next slide, there are a few differences here with the tracing agent. Now, a commonality is that it also uses auto instrumentation, and it also uses the OpenTelemetry exporter to post that data. But let's start looking at differences here. So straight off the bat, you can notice from the diagram that the dependent services also have a tracing agent, whereas in the other one, we saw that the metrics agent was only in the root service. This is because since Horus has been made for microservice applications with the root service, you only install it in the root service, because since every request goes through it, that's where you collect that data. That aggregates and averages out what's happening in the system. The difference with traces is that since traces are made up of spans, like Rich explained, spans happen in other services as well, because they represent operations in a service. So if you were only to have traces in the root service, you wouldn't be able to see all of the spans, which is why that you need to install that tracing agent in every service. And that's why every service exports the spans that are generated in them to the connector. A second key difference is that you don't just generate those traces and spans, you generate and queue them. And it's because, unlike a metric, which generates every interval, say every 10 seconds, with traces, you generate them every time an HTTP request comes in. So that means that if you didn't queue traces, you would be hitting the database every time a request hits your microservice, which would have a taxing effect. It would be resource intensive on the connector and the database. So we've implemented OpenTelemetry using OpenTelemetry tools to queue and then send as a batch multiple traces and spans. So that allows us to take in more requests per second and have our infrastructure still work perfectly well. So now that we've seen Horus agents, let's now start looking at the Horus architecture, at the VPS. So that first part was Horus agent, the only part of Horus that sits outside of our VPS. This next one is the infrastructure that lives in the VPS. And there are 4 parts to it. The first part is the connector. It's just an express server that receives post requests to 2 different endpoints, one for metrics and one for traces. What this connector does is parse and validates data for the schema. So it parses that data coming in and validates it. And on top of that, when it comes to the dates, it enforces UTC on the timestamps. And the purpose of this is to make sure that the times are always on the same time zone, which will then allow us to associate metrics with traces. The second component is the database that the connector inserts data into. Now, we chose to work with timescale for 3 key reasons. The first is that it's a time series database. And this was something very important to us because telemetry data is time series data. It's the key characteristic is that you can sort it and organize it and work with it based on time. The second is that unlike some other time series database, timescale works with SQL. Timescale is specifically built on top of PostgreSQL, which we all work with. And this is especially important because if Oliver and his team at some point need to understand the code or need to extend the code to suit their needs, working with a SQL compliant database is going to be easier, not only because it works with SQL, but because if they have to change the schema, I need to find relations, that's something that works out of the box with timescale, since it's built on top of PostgreSQL. And finally, because timescale has some optimizations built in specifically for time series data, there's great performance and scale that you get with timescale that you don't get with PostgreSQL, for example. Now, the final piece is the UI, which at a high level, you can think about it as a single architectural components, but here we're displaying it as two parts because they're running in two different Docker containers. One is the UI server that is an Express app that makes requests to the database, it queries the database. And the other is the UI client, which is a Next.js app that has React components. And that is what allows the end user, Oliver, or one of his colleagues, to interact and interface with the data in the database. So some key decisions here was decoupling that UI client and UI server, which makes it easier to work with and develop. And this is particularly important if Horus, Oliver and his team want to extend the products later. A second key thing that we saw with Callie is build that association of metrics with traces through timestamps. And the way this happens is that when you click on a metric point, on the front end, we get the delta between the current timestamp and the next timestamp. And that allows us to, by using those two different timestamps, to query the traces in that time frame. And finally, the UI client has several custom React components for data visualization that have worked out to great, as Callie showed. So now let's go back, now that we've looked at the architecture and broken down my pieces, to what Rich was talking about, these telemetry pipeline stages. So this first part is the emission stage. This happens when a customer makes a request, and as the request travels between the root service and the other services. So this is where the telemetry data is generated by the Horus agent using OpenTelemetry tools, those tracing and metrics agents. The second part is the shipping stage. And this also includes these services, because these services not only have the instrumentation that generates the data, but they also have the OpenTelemetry exporters that export that data. So since the shipping stage is about exporting data, processing data, and storing data, that exporting starts at those services, because the dependent services export the traces directly to the connector, and the root service exports the metrics and traces also directly to the connector, all of them through push requests. It also includes, naturally, the connector that processes the data, and then the database that stores the data. And then finally, we have the presentation stage, which is the UI. So it is the UI server and the UI client, which together allow Oliver and his teammates, or whichever developer that uses Horus, to interface with that data. And the great thing about working with Horus is that since we've built it on Docker, like I showed before, with a Docker network and several Docker containers working within it, you can just set it up and run it with Docker Compose up. We have a Docker Compose YAML file that instructs Docker how to spin up these containers and have them work together. So it's very simple to use. So now that I've shown how Horus works and how to deploy it, I'll let Juan take over and finish with the challenges that we face in the development process.
Thanks, Jose. To develop a framework like Horus, we had to solve a couple of engineering challenges and trade-offs. The first one was connecting metrics and traces together. But as I will explain later, this created another problem, time zone differences. Finally, we also had to decide between various visualization trade-offs. A key feature of Horus is a clear link between metrics and traces. But generating related metrics and traces is only the beginning. You have to store and query them while maintaining their relationship. How do you show the right traces? Several observability tools rely on an assigned ID to maintain this connection. When the metrics and traces are generated, before they are stored in the database, the trace is given a metric ID and the metric is given a trace ID. However, this creates two sub-problems. The first one is that if metrics are generated let's say every 10 seconds, many traces have been created in that period. To hold information about all of these traces, a big array must be created. The flow of Horus is from metric to traces. So the metrics need to hold information to point to the related traces. An array of hundreds of IDs didn't seem like a wise approach, especially when that would need to be potentially stored across errors per second and latency. The second problem is about what happens if a metric is related to multiple traces, or if a trace is related to multiple metrics. It's a many-to-many relationship, which is complex to store and query. Some platforms solve this issue by only storing one important trace per metric data point. If the trace passes some checks, for example, it has a status code of 500 or 404, it is chosen as the most important trace and stored. All the traces that the metric data point referenced are discarded. From a storage standpoint, this trade-off makes sense. However, disadvantage is clear: lost information. What if the user wants all the traces? What if there are multiple relevant traces in a single metric? To solve this, we settle on an organic connection, time. Since metrics cover an interval of time, we only have to query traces that fall within that interval of time in order to display the right traces. It's also simple. The problem was that this connection with time raised another issue: different time zones. This caused issues when we're correlating metrics and traces. When testing if the database was storing traces and metrics correctly, we realized that sometimes the metrics would not be well correlated with traces. For example, we would query the database in a particular time interval and see that there were 12 requests made. But then, in that same time interval, there would be no traces. This resulted in the user experience that you see on the screen. The user clicks on a metric data point and is taken to the traces page, but there are no traces in this page. This didn't make sense. If during 10-second time frame there are, for example, 12 requests, there should be 12 traces during that time frame. After a bit more digging, we realized that traces existed, but they were off by a couple hours, either forwards or backwards. What was going on? We found out that there was an inconsistency with time zones. To store traces in the database, we would use the timestamp already provided by OpenTelemetry in the emitting stage, which defaults to UTC. However, metrics arrived at the connector without a timestamp. To create it, we invoked the JavaScript date constructor. However, as you can see in the slide, this code returns a different timestamp depending on the time zone of the machine that is making the call. We had to make sure to generate a timestamp in the connector for the metrics that always had UTC time zone, no matter which machine was executing the code. After doing this fix, everything worked as expected. The last challenge we had to solve were some visualization trade-offs. When Jose was explaining the architecture, you might remember that part of it was our own user interface. However, this was not the original idea. Initially, our plan was to use Grafana, an open source dashboard monitoring solution. In essence, Grafana provided the perfect solution to integrate the presentation stage into our application. It could visualize and graph both metrics and traces, and had the ability to query our database of choice, timescale. The problem was that when we started implementing it, we realized that it was not as easy as Grafana made it sound. For metrics, Grafana worked as expected, retrieving data directly from timescale and displaying it appropriately in charts. However, the only option to visualize traces was to use other tracing solutions different from the OpenTelemetry standard, like Jaeger or Sitkit. When we discovered this, we decided to go with Jaeger. But there were two problems with it. The first one is that it uses its own instrumentation to emit tracing data. This means that we'll need to instrument the microservices with both OpenTelemetry and Jaeger. The other drawback is that Jaeger can only store tracing data in either Cassandra or Elasticsearch. This meant we would need to have another database in the project, resulting in the architecture you see on the top diagram in the screen. This architecture works slightly different to the one Jose presented before. In it, the trace data in Jaeger format is sent to Elasticsearch to be stored. The metrics generated by OpenTelemetry are sent to the connector, which stores them in timescale. To display the metrics data, Grafana queries timescale directly. But for the traces data, it uses Jaeger as a data source, which queries Elasticsearch to retrieve the data. This architecture also requires two virtual private servers to work. This is because Elasticsearch takes a lot of resources and needs its own VPS. This adds another layer of complexity, since we will need Docker Swarm to implement and connect the two Docker networks. After some tinkering, we were able to make this architecture work. However, not all of our problems were solved. First of all, the architecture was very resource intensive. The Elasticsearch server had problems with it, and it crashed several times while it was running. It's true that we're not using a very powerful server, but thinking about our use case, we thought it was best to not need powerful hardware to make Horus work. Also, having two databases could introduce time synchronicity issues, which would have been fatal for the connection of metrics and traces. Finally, we just didn't like the idea of having such a complex architecture because it meant more potential points of failure. After coming together to discuss our options, we decided that the optimal solution would be to develop our own user interface. This way, we will not have the problems mentioned before. Plus, we would have an extra advantage, the total customization of the user experience. When working with Grafana, you have to conform to the options it offers for display of information. However, with our own UI, we could choose exactly what the user sees, from the colors to the data to the different pages. This allowed Horus to be a better fit for the potential users of our application. The problem, again, was that to develop the UI, we had to resolve some drawbacks that had to be considered. The first one is the design decisions we had to take when developing it. Because the options were infinite, we had to be very deliberate to choose the functionality and scope we wanted to have. We also had to ramp up on a couple of libraries and frameworks that we had no previous experience with, which meant an extra engineering effort. We used Tailwind library to avoid writing a lot of CSS, Nivo for the metric charts, chart.js for the waterfall charts, and Next.js, which is similar to React as a front-end framework. After seeing the results of making the UI, we are glad we decided to abandon Grafana and going with it. It made Horus more elegant and easy to use. Plus, it increased the possibilities for future development. Talking about that, although it fulfills all of Oliver's needs, an open source project is never fully finished. These are some of the features that we'd like to pursue in future iterations. The first one is developing more pages in the UI. For example, a page where the user can choose a custom timeframe and view all the traces that happen in that timeframe, instead of having to go through metrics first. Support more languages different from JavaScript when generating OpenTelemetry data. And finally, we would like to test the project further to investigate the hardware requirements for hosting Horus on larger systems. In the screen, you can see the team that built Horus and our locations. If you have any questions, we'll be happy to answer them. I think you can write them in in a box, and we'll see them and answer them.
Brilliant, thanks guys. So I've got one question here from Will, which I think is a brilliant question. Says, it seems like it would have been difficult to build and test this without a non-trivial app. So how did you test out Horus? And I think that's a great question. There were several ways that we did test it. And what's great about building an observability solution is that you can actually get that real-time feedback about how your application is working. You know, you're able to make you're able to make a request on your dummy application, and then you can see is it translating to your own service, to Horus. So we managed to get that real-time feedback from our own application, but we also, one of the major things for us that was really important to get right was to make sure that it was our responsibility as a team and as developers to make sure that that telemetry data was never lost, or that it was always accurate to the events that were taking place in the application. So one of the major testing that we did was load testing using Artillery IO to make sure that when this application was receiving a high number of requests, and those requests again were accelerated and raised over a period of time, that Horus wasn't dropping any of that data. So it was always getting the real-time data accurately and interpreting it appropriately on our UI. So yeah, we used Artillery IO with our application, and that was a success. So we're really happy with that. And then with the front-end elements as well, we used Jest to make sure that the data that we were presenting was accurate to the data that we expected as well. So those were our two primary forms of testing. I'll reach out to the guys in case there's anything there I've missed.
Yeah, I think I just add to that. Another small part that we did too, well, not small, another thing that we did was, so we did use kind of a trivial app, I guess I'd call it, when we started developing everything, just like make sure that works first. But we did also go to testing it with a microservice that was distributed across different DigitalOcean droplets. So it had a root service on a root droplet, and there was other droplets at other services. They all communicated, and they all gave their data, their telemetry data to Horus. So we didn't test it with a non-trivial app the whole way through. Probably, I think it's because it would be complicated, but we used a non-trivial app at the end, kind of after we were more confident, like, okay, this is working, let's test it in a more difficult sphere. So that was just another stage of our testing as well.
Brilliant, thanks, Callie.
Yeah.
A follow-up question here again, an excellent question. So the difficulty of learning new tech standpoint, how big of a percentage was building out the front? And I think I'll pass this to Callie and Juan, rather regarding the front end. From my standpoint, it was a really big moment for us, because, like we said, our original prototype was to use Grafana and outsource that responsibility to them. But actually, it was a really big turning point for us, and we had to spend a lot of time making that decision and weighing out the pros and cons of doing it. And I think that we made the right decision. But I'll pass it out to Juan to talk us through some of the design decisions and why we decided to do it. Juan.
Thanks, Rich. So yeah, we were a bit hesitant on doing the UI, to be fair. So I would estimate it was maybe 30% of the total time. I don't know if you agree, Callie.
Yeah, I'd say 30 to 50. It feels like, yeah, I feel like we kind of got the rest of it done about halfway through. I think we were about halfway through our time when we're like, man, we need to make our own UI. And that was one of the reasons why it was so hard, because we're like, if we make a UI, it has to be nice. And to make a nice UI, that's going to take forever. So, but we iterated through other stuff. So yeah, I'd say 30 to 40%. I'd agree with that.
Brilliant, excellent, thank you. So we got another question here from Katerina. Why did you decide to work on observability, an observability solution, and what other ideas did you have? I'm going to pass this to Jose. So why did we work on an observability solution?
Sure, thanks. So we were doing some general research on different areas, just things like canary deployments, observability, among others. We thought that observability had a lot of potential since, like Rich spoke about, you can describe a telemetry pipeline like a data pipeline. So that was a type of problem we were quite interested in. And then within the space of observability, we did juggle a few ideas of the type of problems we wanted to address. And we ended up going down this full stack APM type solution. Because of, among several things, like my colleague said, Bobby wanted to build our own UI, wanted to work with both backends and frontends. But there were other ideas around there. Initially, actually, we thought more about plugging things together and having an ease of use case, whereas you might have noticed this turned out to be bigger than that. For example, again, we develop our own UI rather than just plugging in something like Grafana.
Excellent. Does anybody else want to add anything to that as well?
I think other ideas, something that I still wish would have worked, but it just doesn't exist. And maybe some other Capstone team could do this, is when we first started looking at observability, we were trying to see if there's a way to connect observability with security. So like figuring out there were security breaches through metrics or traces in some kind of way, which we weren't able to find something that really supported that. But yeah, I think a lot of what I remember is we had a bunch of different ideas, but they're escaping me now. But I just remember we went down observability because we knew that observability is so, like the use for it, I feel like is so clear, but then it's also so difficult to use. So like Jose said, our first goal was just to make it easier to work with and not even make a lot of custom stuff, but that's kind of how it came about.
Brilliant, excellent. So we've got a couple of questions here about Next.js and why we decided to use that. Do you guys want to jump into that?
Yeah, I think we used it plain and simple because somebody suggested it. And we looked at it, and we all have experience with React. And so that was the most comfortable place for us to go. But the person who recommended Next said it's like React, but a little bit easier to work with. And so that always sounds nice. And we tried it out, and we really enjoyed it. It was, for me at least, it felt familiar enough to React that I didn't feel disoriented or confused. I think, I ramped up on it, meaning I could just start using it and actually building our UI with other teammates in like 2 hours. So it wasn't, I guess, scary to use or confusing. But all it really did was, oh, I should do these 4 steps in React. Yeah, you don't have to do any of them in Next. They just happen. And so it was really nice to take away some of the steps you have to do to make a UI. And yeah, we were already hesitant about making the UI. So anything making it simpler and easier, we were on board with.
Yeah, it did feel like a real natural evolution, building on from our skills. It was really, it felt really great kind of working with that technology, being able to use our pre-existing skills in React, and just making that more streamlined user experience for us as developers. So another question here. I'm going to pass this one over to Jose. Great question as well. Multiple different moving parts. And did we have any specific issues when managing connections between containers and other services?
Sure, we actually did. So we were initially developing the different applications, so to say, different parts of Horus, as in the connector, the database, the UI server, and the UI client locally. And then we were having issues with how we migrated that code into Docker. So we were able to set up the Docker containers and the overarching Docker network with Docker Compose somewhat easily. The challenge then became, how do we make what was working locally in our local computers work in Docker? Because in Docker, you have different Docker containers, which are self-isolated and they communicate via HTTP. So they're in different, even though they're in the same IP address, as in the same VPS, they just don't know about each other. Unlike locally, where you can use localhost to communicate in different for applications, different hosts. So that was something that it took us quite a bit of time getting that right, which specifically Juan helps a lot with to address. And it was just, there were just many things about getting variables right, accessing data, what type of variables to use, for example, environmental variables or other types of variables, as in, for example, in Docker, which again just was a challenge, but we eventually overcame.
Yeah, and the thing, just to add to that, I think it was really worth the engineering effort we put into it to use Docker, because we could run it locally on our own machines, we could run it in a DigitalOcean droplet, you can run it on AWS. It gives it so much more accessibility to be used as a product. Okay, great, excellent. Another question here. What challenges did you face working on this project in a distributed team? And how did you overcome those challenges? From Carl. So great question, thank you, Carl. Does anyone want to jump in with this one?
I'd say, that was a concern of mine coming into this team because we're all over the place, right? We have the farthest difference I think at one time was 7 hours difference between us. And I gotta say, so Jose right now is on my time zone. He's in Peru right now, but Rich and Juan were so nice in how they accommodated to the Eastern time zone, and stayed up late and still were able to brilliantly code at like 2 o'clock in the morning. And so that was really helpful. I think something else that helped was we met often, we checked in often. And even though we're far, I personally never felt like, man, what's going on? Or what are people working on? I felt very connected and like we're on the same page, even if we're doing different things. And I think the accommodation of us all meeting together often and doing that was really good.
Yeah, I mean, for me, it's been just such a joy to work in throughout this whole experience with these guys. Even though we've got the time zone difference, you learn very quickly to adapt to like, okay, so what are we going to set aside for today? What are we going to put aside for tomorrow? We solve in our own time independently. So this project has been really rewarding in that sense that we've been able to adapt to those different time zones, adapt to that remote working environment, and being able to work really effectively as a team under those circumstances. But yeah, I think it's been really great. I've really enjoyed it. Some of the problems, challenges though, I think I suppose one of the challenges is making sure that everybody's okay working across those different time zones, as Callie mentioned. Like me and Juan were kind of in that like later in the evening, and just kind of making sure that everybody's feeling good, everybody's everybody is feeling okay at the desk, and making sure that they that it's and having that awareness as well, right? I think that's one of the things when you're not in the same space as somebody, it can be hard to pick up on those things. So again, just having that general awareness. But I think I again, in terms of challenges, no real great challenges, but certainly a really good experience. Juan or Jose, would you like to jump in on that at all?
Yeah, I mean, I think maybe something I would add that I think probably helped a lot was, I think we were very concerned about making it work. And we are very conscious that working remotely can be a challenge because, like Rich said, you aren't in the same place. So it's hard to pick up on what other people are thinking and feeling and doing and so forth. So I think we are very deliberate in trying to create a good dynamic and making it work. I think overall we did quite well, and it probably in large part because we were trying to be very deliberate about it from the start. I remember that we spoke about it a lot, especially towards the start of working together, about how we wanted to work together. But besides like planning it, we also made decisions as we went along to accommodate to what worked best for everyone.
Excellent. We've got another question. So are there any trade-off decisions that in hindsight seem like not an ideal solution? So anything that we went through that might not seem like the best idea?
Yeah, now after, I think Jose didn't mention before, but when talking about Docker, one of the very painful thing was Dockerizing Next.js for a couple of reasons. First, it took like forever. Like it's every time you wanted to generate a new image, it was like 15-minute wait, and yeah, it was a blocking thing, so you had to be there waiting. Yeah, sitting at the sitting on the computer waiting for it to finish. So that really slow us down a little bit towards the end. And also, again, working with environment variables and Next.js and Docker. Again, it was not easy at all. But yeah, like we didn't really check that before committing to Next.js. So we tried to Dockerize everything at the end. So it was like part of optional. So after we had developed everything, we went to Dockerize, and then we realized, oh, Dockerizing Next.js is not fun. But yeah, so yeah, we would probably look for a different front-end framework that is easy to Dockerize.
Great, excellent. So I hope that's answered all your questions. I know that sometimes it can take a bit of time if you have a question, it sort of comes to you later on. So we're all on Slack, so do feel free to reach out to us if you have any further questions, and we'll be happy to answer them. Thanks again for joining us today, and we really hope you enjoyed our presentation, and thank you very much.
Yes, thanks everyone.
Everyone.